Okay, now let's take a look at chemical formulas of compounds. If you remember from before, the formulas have two components. We have the element symbol and then we have subscripts, and these subscripts tell us the mole ratios of each of the elements that's in the compound. So example, if NO2 is our compound, that says I have 2 atoms of oxygen for every 1 atom of nitrogen, which also means that for every 1 mole of the NO2, I have 2 moles of oxygen atoms to every 1 mole of nitrogen atoms. Okay, so if I know that I can figure out what that set ratio is, then, or if I have information to figure out what that mole ratio is, then I can use that to determine the formula of the compound. Now, in talking about formulas, there are a couple of different kinds of formulas that we're going to deal with. Empirical formula is just the formula that represents the smallest ratio present. For example, if we had H2O, that is an empirical formula. However, H2O2 would not be an empirical formula. Its empirical formula would just be HO, because it represents 1 to 1 would be the empirical. Ionic formula, those are always empirical, just by the way that we defined a formula unit for an ionic substance. The formula unit is the smallest ratio of the elements in the substance that defines what the substance is. So formulas for ionic substances are always going to be empirical. A molecular formula is the formula of the substance as it exists in nature. So above here we talked about how H2O2 would not be an empirical formula. However, H2O2, which is hydrogen peroxide, that is an empirical formula. That is how that substance actually exists. Okay? H2O for water, that is both the molecular and the empirical. It is the simplest ratio, and it is exactly how that substance exists in nature. Okay, so thing to remember as we move into how do we calculate empirical formulas is that the subscripts in the formula represent mole ratios, and that they are always going to be given in whole numbers. Okay, so that's key to this process we're going to look at. All right, to get an empirical formula, here is the basic procedure that we're going to follow. You're going to find the mass in grams if it's needed. Sometimes they will give you the mass of each element in the compound. Other times they're going to give you a percent composition, and we'll look at what you do if they give it to you in that way. Then you're going to take those grams of each element and convert them into moles. Then you're going to divide by the smallest number of moles to get the simplest whole number ratio. Okay? If you were taking a math class, this third step, they would call it normalizing. Okay? But here we're just going to call it divide everything by the smallest number. And then if after you do that you don't get whole numbers, you're going to look for a number that you can multiply everything by to get them into whole numbers while still preserving the ratio between each of the components. And again, we'll talk a little more detail about this process. It'll be clearer as we go through some examples. Okay. Here is a rhyme that I came across to help you remember the process step by step. One of the biggest mistakes I see people do is that they'll start through the process and they'll skip a step. So the rhyme to help you remember the steps are percent to mass, mass to mole, divide by small, times to whole. All right, so kind of come back to that as we go through the process of solving. All right, so here we have a brown gas, which is an air pollutant, is found to contain 2.34 grams of nitrogen and 5.34 grams of oxygen. We want to know the formula for this substance. And of course, with this type of information, the best we're going to be able to do is the empirical formula. So we already have them in grams. All right, so I usually write them this way on the page, and you'll see why here in a minute. All right, then convert it to moles, mass to moles, the second step. So we're going to do our molar mass of nitrogen and molar mass of oxygen. And so we get there 2.34 divided by, so 0.167059. And on this step, you really want to carry the values out at least 5 or 6 digits. The reason is that sometimes if you round these too early, you'll over round and you'll get the wrong ratio. So don't round these until the very end, these values. So in this step, we're going to carry them out just to make sure that we don't round past any of our ratios. So 0.33396. Okay, so this is moles. Now we have each in moles. Now I'm going to normalize these values, or essentially divide each by the smallest, which should get me a whole number. And so we get this is going to be 1 there, and then this one 396 divided by 0.1. Whoops, I keep putting that in wrong. 67059. That's going to be 1.999, which is approximately 2. So when we get to that whole number place, if it's very close to a whole number, you can go ahead and round them. And what this says is that my formula then, these are my subscripts, is NO2. Okay, and that is an empirical formula, and that is also a molecular formula. Okay, now here's an empirical formula if we have a percent composition. So say here I have 60.8% sodium, 28.6% boron, and 10.6% hydrogen. Okay, if it gives us percent composition, essentially what we're going to do is we're going to assume that we have 100 grams of this substance. And so if I have 100 grams of the substance, I'm going to have 60.8 grams of sodium, 28.6 grams of boron, and 10.6 grams of hydrogen. Process is still the same. First step is convert to moles. And boron is 10.811, and this one is, sodium is 22.98 grams. All right, so then we're going to calculate our moles, and again, carrying it out 5 or 6 places. 2.64578. 2.64545. 10.559. Okay, so our smallest value is this one, so 2.64545, 2.64545. This one is 1, that one's going to give us a 1, and so that's going to give us 3.975, which is about 4. So my formula then is going to be NaBH4 for that. Okay, now let's take a look. We'll move right along here.